So, welcome to the Deep Learning for Natural Language Processing course. Today's lecture will be about context, and it's kind of the prelude from what's about to come on pre-training and how to use large amount of data to grasp, let's say, intrinsic features from language and use on more specific downstream tasks. So we'll talk also about subword models, more specifically on fast text, but very quickly. And we'll put some more time on how people decided to say, hey, the more context that I have, the better is for my model to learn about the language, and how we can kind of look counterintuitively on that. Because the first thing that we think about context is, I want larger structures. Words, sentence, phrases, documents, and so on, and things might be a bit different. So far, all the models and techniques are assuming that each word will have a single static vector representation. Later on, we'll change this static notion of word embeddings to something more dynamic, in which a vector of a word not more will depend on just, let's say, the co-occurrence of two words, but then it takes into account the entire context or the entire sentence of that. But be that as it may, these vectors so far, they're either from a randomly initialization, as we saw for our neural language model, or pre-trained word embeddings such as word2vec, glove, and so on. We also saw that some recent works try to represent, well, not that recent to be honest, they try to represent the entire sentence directly. So we saw on paragraph vectors, if you don't remember, that's doc2vec, in which instead of just looking to the co-occurrence of word A and word B, they would take the entire sentence. And then how we said that, how we can expand this notion, in which before we had co-occurrence of words, sentence, paragraphs, and documents. We said, how can you average the vectors of a given document and have a good representation? But the thing is, there's just so much you can do, right? You move from words, sentence, paragraph, documents, and what is next on that? In that direction, people thought, hey, instead of moving, in this case, from left to right here, from a lower representation to a more higher level representation, why don't we look the other way around? So instead of looking forward in the representation, let's look backward in the case that, let's do this here, yes, in a way that from words, we can define subwords, characters, bytes, and so on. And it might sound counterintuitive, but if you start thinking about those models that have a lot of features, a lot of parameters, they're able to have a grasp on, let's say, correlation between words and relationship between words that we cannot. So instead of going higher level representation, why don't we go backward and say, hey, let's use this amount of features and try to represent those words and the inner components of those words. Although for us, it might not make a lot of sense, maybe for this model, they can grasp something that, again, we can't. So, and you would be surprised that this pretty much here is, I would say, is the state of the art on how to represent whatever document that you have. You always break the words either into word pieces or subwords, characters, bytes, and so on. And just to give you an example of how this looks like, for example, we have here the word morphology. If we look closely, we'll see that the word itself is composed of a bunch of different elements. So morph here is the base, we have a connector, log, it can be a base again, account, reason, the y is a suffix, and although this here is not that interesting, the combination between the subtokens that you have in these words, then they allow for something a little bit more interesting for us. To use an example of how subwords, they do mean a thing, if we take the word unfortunately, depending how you break these words and how much you use those subword representations, you can concatenate and formulate entirely different words with different meanings. And this is quite relevant for us, because if we have, let's say, to represent all of these guys right here separately, we have to, let's say, bloat our vector representation. But if you keep a grasp on how the subwords are formed, you can concatenate, play around, and let's say provide any word you want, at least in theory. If you don't have the subword or the subtoken, this doesn't happen naturally, of course. But yeah, let's take a look a bit closer on this. So, and you might also, I mean, on top of represent the subwords, we can also deal with words that don't necessarily are captured easily. For example, I think I mentioned this in the very first lecture when we talk about text representation, how you deal with some words that, for example, are not white space separated, like life insurance company employee, and this time I will not dare to say these words. So if you have to store this entire word right here, it is a bit troublesome, but then if you're able to break this down into some subtokens, things might get easier. Depending on the task that you're handling, you're also able to deal with words that, let's say, they don't exist in any dictionary, so they are neologisms. For example, let's say you're doing sentiment analysis on Twitter and you have, despite the constant negative press of Kofefe or something. I probably remember who tweeted this a couple of years ago. Also, you can deal with misspelling words, and why that? Because words that usually mean a thing or they're written the same way, most likely they will also have similar relationships. The same rationale that we had for word to vec, that the words that co-occur most likely have the same meaning, the subwords that are similar somehow, they also have similar meaning. Of course, there's exception for all those rules, but still, if you're dealing with a model that can break down words, you can deal with stuff like this. Now, if this here will mean something, that's a completely different story, right? So, more specifically on subwords and character level models, word embeddings, the exact way we learned, they can also be composed of character embeddings, and this allows us to generate embeddings for unknown words, as we just saw. Also, as I just said, similar spellings, they share similar embeddings. In theory, this here, it's debatable. And why it solves out of a vocabulary problem? Simply because, okay, if you don't have specific words, but if you have the components of those words separately, yes, okay, you can, let's say, average the vectors, sum the vectors, and you can represent that. However, if you don't have the subtokens from that specific out of the vocabulary word, then you cannot compose the vector for a word that you haven't seen before. You can, however, go a step further, and instead of using subwords, use a character representation, and then if you have any alphanumeric character, you have an encoding for all of them, and you can concatenate them, sum, average again, and then you have the representation for that word that in theory does not exist, all right? Also, those two methods, the subword and the character level models, they work quite good. In fact, I would say after 2017, 18 for that matter, this is pretty much the standard. People don't usually now, if you, I mean, probably already playing with your models in your project, you see that the very first step is you have to tokenize for a specific model your words, and you break down into some weird characters with hashtags, subparts, and so on. Virtually all the models nowadays, they use this. In fact, they're based on a technique that was not inspired by deep neural networks, but we'll take a look at that. And this is really cool because when you see those weird endings or suffixes and prefixes when you tokenize your word, for us, it doesn't mean a thing. But as we have that many parameters to be able to capture those relationships, for them, when I say them, the model, it does help things, all right? So, byte pair encoding. I think this is probably a very underappreciated work. If you're working with pretty much any transformers, you see this kind of encoding. The thing is, there's a work published in 2016, and it's here to prove that not everything in NLP is about neural network. 99.9% is, but there is an exception to every rule, in a way that they come up with an algorithm for you to represent your words according to the characters and the subcomponents of every word in the form of a dictionary. It's based on a compression algorithm. It is similar to Huffman coding. It's not the same thing, but we do provide the paper there for details. We'll explain how it works. There is a big requirement on this, but we'll talk about this in a minute. So we pretty much start with a unigram vocabulary of all the characters in our data. So we parse all the words there, and we visit and extract every character, and then we start moving upwards, in a sense, the longer anagrams on that dictionary that we have. And then we keep doing this until a certain threshold. And yeah, you do this to a certain count, and of course, the larger your vocabulary / dictionary, the larger will be your list of characters, subcharacters, and so on. And how does it work? Imagine that you have a text made of these words right here, lower, lowest, widest, and whatever, and we already parsed that. We provide the count for all those words, and now what we do is we start creating a new vocabulary composed first of all the unigrams present in our dictionary, and then we start visiting every single subsequence after the unigrams that have the highest count. So in this case right here, the bigram ES has 9 occurrences. Then we keep track of this. The next one, well, you can move for the highest trigram, or you can go over all the most frequent bigrams until a certain threshold. This is just a toy example. And you keep doing this until a certain threshold is reached. I don't know, 200 words in your vocabulary or something like that. Okay? Yeah, and you can check out a good example from Professor Dangerevsky right here. Yeah. So, as I said before, this algorithm, it runs until a certain size is reached. So it's quite determinist in this sense, in a way that it works with a long piece segmentation. And this is the biggest requirement that you have. And this is how we see already how low resource language and high resource language, they start to get impacted by new technologies. So let's say all the transformers, they use byte pair encoding. And the very first step on that you need a good tokenizer. So if you're working in a language that does not have the tokenizer, you're already in big trouble to use, let's say, new architectures. In this case, if you're working with them and this low resource language and you cannot tokenize them to separate the words somehow, you cannot run this algorithm, which is, again, quite troublesome. This was really popular in 2016, 18, and now everyone just take this for granted. A good example, we have a project working with Old German, and they wanted to use AI/transformers in whatever technology problem they had, and they were asking to use, for example, BERT on it. Because of how the Old German is composed, we cannot use existing tokenize for, let's say, New German on that. So right now, one of the challenges in this project is to come up with our own tokenizer to be able even to start using new technologies. Okay? Yeah, and we'll see that many recent architectures, they use this encoding still, right? Moving on subword embeddings. Probably you remember this clever guy right here. So from words, he moved to documents and now say, yeah, it doesn't work that good. The truth of the matter is doc2vec was really good for like 2-3 years. And after that, people saw that, yeah, that doesn't scale, doesn't achieve that many good results. And they come up with the idea of moving a little bit backwards with subword encoding. So pretty much this is an improvement over word2vec. So nowadays, if you have a problem that can apply word2vec, start with fast text. It's an improvement on every single thing that word2vec does. It's more efficient, it has better results, it has a really good multilingual embeddings. Also, they have a really nice API that you can control how many dimensions you have for every word representation. So let's say you work in a model that's too heavy because it has 1,000 dimensions. You can really just rescale the model with lower dimensionality with one line of code. So it's quite handy. So in the improvement on word2vec, there is no sentence representation. This still kind of happens in word2vec, in fast text, but not that prominently. And morphology, now we take care of this by working with subword tokens. But yeah, let's take a look at how it works. So imagine that we have whatever sentence that we have here, on top of everything that we did for word2vec. So we have the context sliding window, we look for the context word, predict the center word, everything's still valid. But now, for every word that we're trying to predict, we're going to break it down into some specific sub-word length, in this case here of 3. And every word that we're breaking down in sub-words, they will have a special token. I think we mentioned about this a bit in the past, like how the insertion of special tokens to the limit where something begins and ends, they start being used more often. This is another example. And then the way they do, they have this anagram that they call character anagram representation, but it's nothing more than subwording. And then the word itself, and they just sum all those vectors to have the vector representation for that word. When you say, hey, is it sum a good approximation? Yeah, for that case, yes, it is. Can I average this? Yes, if you want, you can average. If you get the sub-character representation, and then you provide the actual word and you average all the vectors, you can also do this representation if you want. But in the original paper, they just sum that. This is just repeating what I just said. Nothing new here. Oh yeah, they do use a hashing function to store those n-grams here, simply because this grows a lot. So imagine that for every word that you're parsing, you're breaking down on specific subwording, so they have a function to make this a little bit more efficient. Yes, so this subword representation allows fastText to explore words out of the initial vocabulary, again, to some extension, simply because if, let's say at test time, at inference time, you're trying to recover a vector for a word that you do not have the subcomponents, you won't be able to form the new word. If you have the subcomponents there, that's good for you. If you don't, well, that's bad luck. They did evaluate that in a bunch of different tasks like sentiment analysis, partial speech, word similarity, text classification, and the amount of papers that was just the same way that happened with word2vec, and they had the era of x2vec. They tried to code everything in this vector representation and simply apply in tasks. It happened the same with fastText. It happened the same with BERT that we're going to see in 1.5 lectures from now. And every wave in NLP, you see these derived papers just taking those technologies and apply directly to the problem, which again has nothing wrong. Just keep in mind they're just applications. This vector representation was widely used as a vector initialization for neural network approaches, and we'll talk about this again towards the end of the class, simply because now we have even a more powerful model to represent not only the relationship between words, but the relationship between the subwords of that word. And that provide a better representation than standard random distribution initialization for our vectors, okay? They do have, if I remember correctly, 160, 150 languages encoded. So they have multiple different languages for their encoding. So you can just download and use either in text file or binary. The API also allows you to do this. What happened in practice, especially in the beginning when this, let's say, this gap years between those word2vec approaches and then later on transformers, you would see a lot of models using kind of a hybrid representation in which they just don't use the word vectors, but they also use subwords or character levels and so on. And the idea is the more, let's say, diverse representation you have, hopefully the better you'll get in whatever end task you have. And as a spoiler, they do get better. So if you're working with a model, instead of just using the words, you concatenate in your representation. Words, subwords, and character. This model is way more powerful than you just use words for that specific architecture, task, data, and so on. Okay? Yeah. So, more context, because I'm not that creative with titles. We'll see from now on how people got a grasp on this idea that, hey, the more context that you have to represent the relationships, the better it gets. So how can we leverage this? And we already learned something that taught us how to look at the context Remember when we talk about neural language model? So that was already doing this. So people decide to take this to a different level, and it actually worked quite well. But just some recap. So far, every representation that we have been seeing here, either with word embeddings, sub-word embeddings, and we actually didn't talk that much about character. Well, byte pair encoding is somehow character embeddings. They always have one representation per word, so it doesn't matter in which context you're using those words, they always have the same vector, the same numerical distribution there. We saw, however, how to expand this notion from one representation to multiple representation with multi-sentence embeddings through annotated data, lexical databases, knowledge database, and so on. But the truth is this doesn't scale that well. So you still rely on a bunch of structured knowledge organized already. So this can be a bit troublesome to deal with. And then we fast look here into fast text and sub-word representation, and also with character level that we can represent the inner aspects of our words, but the truth is they all share the same problem in which they are static. It's really hard for you to, after you have your pre-trained word embeddings, for you to say, hey, this representation is nice, but I need to adjust those numbers a bit. If you put this into a neural network architecture, yes, with training, you can move those values, you can wiggle them, but with those representations that we just saw, this is simply not possible. Although there is a paper, I think it's called World Earth Move Distance or something like that, and retrofitting word embeddings, this is from 2017, in which they have a very custom architecture that after you pre-train your word embeddings, you can retrofit them and make them better according to whatever new data that you have, but it's quite custom design. It's not that easy for you to apply in a bunch of different tasks and scenarios, all right? So just to illustrate this a bit better, imagine that we have all those sentences. It doesn't matter how you're represented right now. If we take a look at the word record or record here, what can we infer about them? That it doesn't matter how we're using. So the record of the runner was amazing. Did you listen to the latest record? We should record that, and the record was otherwise anyway. So what can we infer about these vectors in this word record right here is that it doesn't matter where they're applying, they will have the same value, they will have the same distribution. And this is not exactly what we want, because depending if I want to get the vector representation considering this sentence right here, the first one, I want a different representation than the last one, simply because those words, they do mean different things, right? And in that direction, of course, this is a very cherry-pick list of publications. There's way, way more between those, but I would say especially these two last ones right here. There's another one here in the middle. They were quite important in a way that, okay, we have good representation, but how can we make it better? Let's use context for that. And what is the thought behind it? So the first one here from Diane Lee. So why don't we do a semi-supervised approach where we train a neural language model on a large unlabeled corpus rather than just word vectors, and use it at the pre-training for a sequence model? So they will already start talking about large unlabeled corpus, how we can harvest the power of pre-training. And I'm highlighting this word here because this will be even more prominently explained in the last lectures, right? Peter's, this is not the Elmo work, but subsequent work from that Elmo is really relevant. We'll go over it. So they want the meaning of a word in a context, but they also want to learn whatever task that they have only on small label data, because what would happen before is you need a lot of label data to do your task. And they say, yeah, it would be nice if we didn't have to rely on that much annotated data, just a bit, and how we can cope with this gap between no representation to a very specific representation. The idea is to use the same idea as here, large unlabeled corpus, in a way that this will probably cope with this, let's say, quote start really between quotes here. And then Howard and Reuter, probably you know, Reuter is quite famous. They had the same general idea of transfer neuro-language model knowledge, but then they applied this to text classification. And this is probably one of the first works that they talk about pre-training, intermediate training, or pre-fine-tuning, or post pre-training, and then actual fine-tuning. Yep. But then you're going to have a representation for every single word sense. You need to know beforehand all the senses of that word, which might not be the case in your training. Let's say the training for the word animal, for example. In Word2Vec, you have around 15 different word senses because you really know the English words. So let's say in your training, you just touch 10 of them. But then whatever test case you have the 5 that never occurred there. So it's quite hard for you to disambiguate that. Okay, and with this kind of approach, there is a hope that the context will tell the meaning of that word, not specifically such as here's the word, here's the definition as in a dictionary, but the vector representation will allow you to, whatever meaning that word is, it will be encoded according to the context that that word is placed. Okay? But then let's go over some of these works right here, and then we have a better idea. So, this is a semi-supervised sequence tagging with bidirectional language model, and you can pretty much already say, wait a minute, you said that bidirectional LSTMs, RNNs, they do not work for language model. Yes, kind of-ish. We'll see that for them also the backward pass didn't help in that sense, but we'll get there. So, a general semi-supervised approach that combines word embeddings and neuro-language model. So they have two different representations. In fact, they have a third one also on top of that. And they use the neuro-language model pre-trained on a large unlabeled corpus to compute an encoding of a context at each position in the sequence, and then they use that in a supervised sequence tagging model. And we'll see some details. The idea is whatever word that I have in whatever text, I have two different representations. The first one for the word itself, word vectors, and the second one for the language model. And I use these two representations concatenating to my end task, in which I train in this end task in the small label data. And how does it look like? This is directly from the original paper, by the way. So we have unlabeled data. Doesn't matter from where, Wikipedia, I don't know, Wikidata, WordNet, so on. So they pre-train word embeddings and a language model. So we have two representations right here. And then they concatenate these two representations, and then they use this into the sequence tagging that they have. I don't remember if it was sentiment analysis or just sequence tagging in name intent recognition, but in any case, they do use this dual representation. They concatenate this to represent whatever word they are dealing in the sequence. And here we can have a little bit of more details on this. So imagine that we have here the sentence, New York is located. So what they do, for every word, they have two models. One, the pre-trained language model, and this here that they train the word representation from scratch, and they have two different representations. One, they use character embeddings. They're using CNN and RNNs to do this. I guess this validates the point why we should cover a bit of CNNs if nobody has ever seen that. They also embed the token directly, so the word new here, not just the characters it's composed. They concatenate this into in one embedding, put that into a bidirectional RNN, and then the hidden state from that by RNN, they concatenate with two passes from their language model, one a forward and then a backward one, and that one they put this again into another RNN, and then they use this last hidden state that's composing from the word token representation and the language model that they had, and they do whatever sequence tagging they had. So the last hidden state representation that they have for the sequence takes into account the backward, the forward pass, and also the word / token representation they had. right? Yes, some details, and you see that this list of details on approaches and architectures, they're going to get bigger, bigger, and bigger, because usually when you take a look into this paper, the description of the technique is, I don't know, half of a column, and then they have an entire 30-page appendix about how the details of the implementation. Be that as it may, so some observations in their model. So the language model is trained on supervised data, does not help at all when they're working with bidirectional language model, and this corroborates with what we talked about, I guess, 2-3 lectures ago, in which if you're doing language model, the backward pause, it doesn't help that much, and they have this in their results. They trained this into 800 million tokens on the 1 billion word benchmark. This was quite famous a while ago. And then the projections that they actually used to represent the words is around 500 dimensions. This last part is not that relevant because we'll see this escalating quite exponentially in the last years. So they train in 32 GPUs, but we'll see this is peanuts if you consider what's happening right now. And then a direct follow-up from this project, probably you heard about this work called ELMO, embeddings from language models. And aside from starting an entire wave of funny names and papers, they had a really cool idea in which this is pretty much the breakout version of the paper that kick off the word token vectors or context word vectors or dynamic word vectors. And they got this best paper award on the NACL 2018. This is, I would say, top 2-3 conference in NLP to get a best paper award in any of this conference. They are pretty good. And this will date probably this lecture, but if you're working for conferences, the top conference in NLP, pretty much ACL, which is the main one, the second one, MNLP, which is as good as ACL, and then you have the chapters from ACL, NACL, AACL, ECHO, and so on, and then you have the others following. So, how they do this? They learn the word token vectors using long context, not just context windows anymore, and they learn a bidirectional neural language model and use all its layers in the prediction, different from the words, the methods that we seen before, in which they were using the very last layer to represent your word. They saw, hey, if we put more layers, why not we use all the inner layers or the inner representations to have a better grasp of the context for those words that we have? And this actually worked really, really well and became pretty much the standard. So, some details, Elmo analyzed the words within the context and then they are used in a way that if you're using their API, for example, when you provide a sentence and you are trying to grasp the vectors of every word, you see that this vector representation from that word, it changes depending on the sentence or the paragraph or for whatever that matter, the document that you send. It has a limitation, of course, but you most likely not get the same vector representation for that word. If you're using the frozen embeddings, what happens in practice is we get this frozen or this pre-trained model, you put this in a neural network and you continue the training for whatever end task you have, okay? It is also character-based representation, allowing the model to form representations from out-of-vocabulary words. I would say this is a direct improvement from fast text. Fast text, you still struggle to represent words that you do not have in your training set, even by subwording. But here, since the initial representation of words is made from characters, it doesn't matter what you provide, you will have a vector to represent that. Are they all useful? Most likely not. So if you provide whatever gibberish there, even if you put like period, period, semicolon, asterisk, you're going to get a vector out of that. You can use. Doesn't mean it's going to be meaningful in any way. And I think, no need. This model does not need to have a word dictionary like the other approaches, simply because you use the characters directly. So, some details in this technology, this architecture. They use just 2 BILSTMs to represent their words, and they use a CNN to have the initial word representation, but then they don't use the CNN anymore. They use residual connections, if you remember, the one that connects directly the input with the output there. And then the tie the parameters of a token input and output in a softmax and tie this between forward and backward language model. I think the diagram will be a bit better. We'll get there. So how does it work when they represent their word embeddings? The very first thing is Elmo word vectors are computed on top of two bidirectional language model, more specifically on two LSTMs. In a way that they use a character level CNN to represent the word as an input, and then we use that representation into a forward and a backward RNN. That's the very first layer. Then the output of both these RNNs right here are combined into intermediate representation, and we use this intermediate representation into another forward and backward LSTM. And then the final representation that we have, we use the weighted sum of all word vector representations. So the first layer, the second layer, and also the word as an input. So we use all the three of them, make a weighted sum, and this is the final representation. Can I access the, let's say, intermediate representations for whatever reason? Yes, you can. Depending on the API that you're using, you can probe each layer and extract that representation for your task. And hopefully remember that we talked about this a couple of times, that the higher you go in the amount of layers, different aspects are being captured. So lower level layers, they catch lower level features, and higher level layers, higher level features. So how does it look like? We have our raw word vector representation. We put this into a forward and a backward pass. This is our first layer. Then the output of each of these RNNs, they are what we call an intermediate word vectors. And then we use this again into another layer. And then we use all these intermediate representations, the last one after the second layer, the intermediate one from the first, and then the raw word vectors into a weighted sum, and then we have the Elmo representation, right? Take care not to fall in the trap that, hey, I have here my pre-trained word embeddings from Elmo, and it should be better than all the previous techniques, because, you know, recent work is better. Okay, if you don't continue the training that in whatever end task you have, those pre-trained word embeddings, they might not be that useful. You want to continue training whatever label data that you have, but you're interested in that in this representation. Okay, this is just to show how this is represented. So after you have your bidirectional language model representation, you concatenate again the input, the forward, and the backward, and use this for whatever end task you have. And we'll get there, but all the tasks that they were playing around, they were about classification tasks. So in a way that you don't need to generate new text. This is an encoder model. Later on, we'll talk about the difference of encoder, decoder, sequence to sequence, text to text, and so on. So they're not generating any new text. They're simply using the encoding that they have to whatever classification test they had. I would say up to this year, there is a standard, this year 2023, there is a standard consensus, was at least, which architecture you use for specific groups of tasks. If you're working with classification, usually, and I'm saying this really between big quotes here, autoencoder models, they perform better. If you're providing text generation tasks such as summarization, translation, and so on, encoder, decoder, or just decoder are better. If you, or sequence to sequence or text to text for that matter. However, in the last year, pretty much those decoder only models or encoder decoder models, they have so many parameters and they're growing so large that they're always, not always, but they are starting to do classification tasks better than encoder models. So this is still, it's kind of a gray area, but in any case. So first they have the task that Elmo play around. So they created their language model to have the initial representation for each word. And then whatever end task that they were playing at that time, they will use that representation in that task. And how they did that, they pretty much freeze the weights from Elmo, then concatenate this last, not the last, the classification, but before the last one, into the task-specific model, which they continue to train. And some details about this approach of, okay, we take the representation, we concatenate, and whatever architecture we have and continue training, this is pretty much the standard using in any model right now, in which you concatenate into the intermediate layer into whatever end task that you have. Tag LM did the same thing. And their representation, their representation from Elmo, they will apply in many NLP tasks. And it did work better in virtually any task that they were doing at that time. This is 2018. Probably next class we'll get to 2019 content. So question and answering, natural language inference, reference resolution, semantic similarity, name-entity recognition, all of them, they beat state-of-the-art results, which is pretty neat, okay? Oh yeah, this is more to help study later on. So their layers, they also had some ablation study in a way that lower layer, they saw that were better for lower level syntax. For example, parts of speech, tagging, syntactic dependencies, name-entity recognition, all those tasks that they rely on syntax, the lower levels, they were a better representation. So if they use that, it was better than they use the weighted sum representation, because this happens later on also. The more tasks you have, the more you try to put in your language model, you have to take care with something called catastrophic forgetting. And this happens a lot in most task learning. The more stuff you try to put there, it's hard for you to remember the, let's say, the basic representation. So let's say you were working with, in some works they do this, they're working with 100 tasks. How can you guarantee that every new task that you're training, you have a good, let's say, learning period for all of them? We're not touching that much multitask learning, but it's a really, really interesting research area. Again, and then also they saw for higher level layers, they were better for higher level related tasks, more on semantics, so sentiment, semantic classification, question answering, inference, and so on. And then looking at this work, people start thinking, okay, they accomplished so much with those two block of layers, 4 if you count that each of them they have backward and forward. Why not we start including more layers on this? And actually that was the direction that some people took. So this work, universal language model fine-tuning, it's probably one of the first ones to actually start playing really hard. There's previous work on transfer learning and transfer knowledge, but they brought this more prominently on NLP in a way that let's use the general idea of transferring neuro-language model from whatever unlabeled text. But instead of going directly from an end task, let's have someone in the middle to adjust this model a bit. Because what would happen, and this also is true for older models such as Word2Vec, at that time not many people could replicate that, so they had the pre-trained word embeddings, and you would apply directly in the task that you have. However, if those things are too far apart, the initial corpus and the end task, it's kind of hard to make a good use of those vectors. So what people thought, in this case this work, let's have something in the middle, which is a text that is different from the unlabeled corpus that you had, but it's a bit closer to the end task. For example, you train your language model on Wikipedia, but then your end task is about doing, let's say, political media bias. But in your training corpus, you never saw news article. So what you do, you continue training your language model and whatever news articles that you have gathered from News Analyze and whatever source, and that will probably take the general representation that you have closer to the end task. And this is the 101 on transfer learning, pre-training, and fine-tuning. But we'll go this in more details. But before that, Well, I just talk about how the idea is here for this work, and the general idea for transfer learning. So their language model is trained on a general domain corpus to capture general features of the language. And this here, depending on the language that you use, you can also do a transfer between different languages. Let's say you're working with different versions of German. So although they are different in their essence, they do share similarities. So let's say you're working with a specific task in which you don't have that much corpus from Old German, maybe with Middle Old German, that you have more text, you can use that in your end task. But after the general domain corpus that you train your language model, they continue training that language model in a target task, in which hopefully we'll be able to capture features closer to the end task that you have. And then at the end, they use the classifier to fine-tune the model on the actual target task. But later on, we'll talk about transfer learning in lecture 10. So this is pretty much their architecture, in which their language model on the pre-training phase, they use, I don't remember the general corpus they use, I'm sorry. And then after they train the general language model, they continue the training on the target corpus, the same task, and then at the end, they use that for a specific task on document classification. And however, they do have details, a bunch of them. So it's not that just straightforward. Because they were using more layers than the other case, they did have specific learning rates for all the layers that they had. They also introduced these two concepts. One is called slanted triangular learning rates, a fancy name to say that they adapt the learning rates according to the task and layer that they're using. Also, and how does that work? First, they increase the learning rate and then starts decaying according with a specific schedule. They also have what they call gradual unfreezing, in a way that they don't fine-tune all the layers at once. They do this layer per layer, so you don't get in trouble with the catastrophic forgetting. But you can ignore this. We won't cover this right now. Also, you will see that things start to get hairy on the training and number of parameters. So they do use, in this case, a reasonable size language model that was trained only in 1 GPU day. If you compare now with models such as GPT, GPT-2, 3, 4, whatever, BERT, we'll see that they have way more training days and way more money was spent on this. If I remember correctly, I think it was GPT-3 at the time, and the hardware that was trained, they spent around $11 million or something like that. Today, if you make a comparison, it's cheaper simply because the hardware is better. But we'll talk about this training in a minute, and also in the very last lecture. They had a lot of care in the language model fine-tuning. In recent works, they're just collaborating with this view, and people take a lot of care with the language model phase. Why? In the beginning, people were not that keen looking how much duplication you have between the data that you pre-trained, because people will take this as granted in your final task. But the thing is, the more data you have, most likely you will have some contamination between whatever language model you're doing and your testing. We already talked about how this is bad science, and you say, yeah, this doesn't happen anymore. Yes, it does. I think the last model from GPT, not 4, I think 3 or 3.5, if you take a look in the original paper, they say very boldly, yes, there's huge contamination between the data that we use in the end tasks, because it gets really hard for you to deduplicate that information. If you use the entire internet, you have pretty much a dedicated project to clean your data and make sure your training tasks are well defined, fine-tuned, and so on. Again, they did have a lot of care with language model fine-tuning. As we saw, they have different pre-learning, different per layer learning rates. They have an algorithm to adjust the learning rate according to schedule, and so on. We have more of the details here, and what they use for their classification in the end was a mix also from hidden states, in a way that they used the very last hidden state, a max pool from all the hidden states, and a mean pool from all of them. So they used those three hidden representations to do the classification in the end. Okay? Then things start to get a bit complicated and hard to track. Why? Because people start to realize, hey, this architecture here, the more data we put, the more you compute, the better it gets. And when you have something like this paradigm, what you do? You start feeding data, non-stopping. And this is actually what's happening until today. So at that time, UL and FIT was training 1 GPU day, and then GPT said, okay, now I have more data, and I trained 200 4 GPU days. And then BERT came in 18 and said, hold my beer. I trained 246 TPUs. At that time, TPU was around 15, 20 times faster than a GPU. GPT-2 came along with more training and so on. And what does it mean that they're training more and more days? It means that we have more parameters now. We're able to capture more relationships between whatever data that we're feeding there. And hopefully you can see the pattern, how things go faster now. So if we consider the first version of GPT-2 with breaking there the 100 million parameters threshold here, and right after 1 year, we are going from 100 million to 11 billion parameters. And this is kind of a spoiler for later lectures. Do you see a potential problem of having that many parameters and training time? I mean, yep. Mhm. That too, they do overfit a lot. Also, the training time and the cost for this is a really important question. In the last years, you have something called green AI and red AI that people are looking really close into this because someone has to pay the bill. It doesn't come from thin air, this energy. It costs a lot of money and a lot of electricity to run those models. I cannot stress this enough. On top of all of this, by having that many parameters, you have to have as much data as you can get. And if you feed that much data, you start capturing all the biases, all the problems, and everything that we convey in text. It doesn't matter if this is right or wrong, if the information there is politically correct or not, it will be embedded in those parameters. It will be there if you don't take care of somehow the biasing, the duplicating, or cleaning your data. This always transfer to those models, and the same way you scale them, you also scale everything that you're putting there. So imagine that every, let's say, feeling, emotion, semantics that you put in a text, if you put in those models that have that many parameters, imagine how many nuances those models are able to get. And this gets tricky because, again, this gets maximized. And this is really, really concerning. Also, just some more new models. Right now, I think one of the largest one has 1.75 trillion parameters or so. Here we can see a bit more graphical on how those models are growing. And by the way, it becomes an arm race between big players. Because on top of all of this, look who is leading this, by the way. It's not like university has money and resources to keep doing this, unless, of course, you have a really good collaboration with some labs, which there are places 100% sponsored by companies. But anyways, this here gets more and more restrictive. Of course, you do have models that are able to distill the knowledge of large language models, and they have their place. However, they can just go that far. They're really good, first of all, imitating large language models in a way that, hey, this model here uses 5% of whatever X model and does the same thing as the large one. Yes, it does the same thing. It imitates really good. But now if you have this distilled model to generate, really between quotes here, new content, does it do it right? Does it provide a chain of thought good enough? Not really. So because you have that many parameters, you're able to go simply further. As for right now, maybe 2 months from now, we have a new architecture that doesn't require that much. And yeah, things get way, way, way more crazy. Just to give you some idea, in July, we're going to present a work that we have, and that pretty much talks about the presence of these big players in NLP. And to have an idea, the number and the presence of industry, when I say industry, being companies, they grow around 180% in the last years, relatively from one year to another, of course. And imagine that if you have to run those models by yourself, it's not that easy, which means that you're going to have to use the pre-trained models to do whatever you want. So it's not like actually you're choosing what you can do, you're choosing where you can apply them. But now to become with, let's say, to merge with your own architecture, your own data, then this is becoming really, really a very selective club. All right? But we'll explore way more about this in the next lectures when we talk about bias, ethics, and so on. And by the way, don't get me wrong, I like these models a lot. They solve a lot of problems that we deal with. But just keep in mind that it comes with a price. Don't think that this comes for free, right? And yeah, that will be all for today, okay?